Thank you very much and welcome. Welcome everyone to the webinar in which we're going to talk about a very important topic in our industry. Today, it is all about the robust manufacturing of photonic integrated circuits and how we can do that all together. We have a spectacular lineup of speakers that are going to rank over all the important parts of the value chain. Many of you were at OFC this year, and we did realize that we have a huge challenge in our industry. Current data centers cannot manage the traffic that AI is going to bring to them in the coming years. And for that, depend on the physical layer. And we know how to do this. We just need to work together. This is the purpose of this webinar. What you're going to witness is how companies can have a piece of the puzzle and how bringing all together can solve these huge challenges of having this robust manufacturing of reliable integrated photonics in this AI era. Together with me, I have companies like AFL, like Global Foundries, like IBM, like IR Labs, Quantify Photonics, Teradyne. Let's see, let's understand from them what challenges they have, what solutions they have, and how each and one of you in the room can help them be successful and can help the industry integrate their technology. Today, I'm going to have Nick Angra, who is the Global Product Lead of AFL, who's going to talk to us about his work for the Advanced Photonics Coalition. Afterwards, Vikas Gupta, the Senior Director of Product Management at Global Foundries, is going to talk to us about the advancements in silicon photonics and how those advancements are matching the demands on ultra-high bandwidth and reliability from the data centers. We'll continue with Alex Jantapositsky from IBM in Bromont in Canada. He's an expert on the packaging and assembly for volume production of complex photonic integrated circuits. But when you talk to volume production, you need contract manufacturers. And the most important, the biggest one in the world and in the room today is Jabil, who will be represented by Giorgio Cazzaniga. You cannot do this if you don't have proper interposers. And the best interposers in the world are manufactured by IR Labs. Scott Clark will talk to us about this. And then afterwards, we have everything packaged. And with the right interposer on it, we are going to test it. And for that, we had the capabilities of Quantify Photonics and, of course, of the giant Teradyne, represented by George Urtate. Thank you very much, all of us, for being with us today. With no further ado, let's get the ball rolling. Let's get things started. I would like to welcome to the room and to the floor Nick Angra from AFL, who today is going to talk to us about the work that he does for the Advanced Photonic Coalition. Thank you very much, Nick, for being with us today. The floor and the attention of a very large audience, the attention of everyone goes to you.
Thank you very much, Jose. I'm just going to bring up my slide deck here in just a second. Thank you for the introduction. Guys, can all see my slides okay?
You go to presentation mode? Yes, perfectly clear.
Okay, excellent. All right, thanks once again, Jose. Good morning, good afternoon, good evening to everybody. My name is Nick Angra. I am presenting today as the Board of Director for APC, and I'm also the Working Group Chair for multi-core fiber. That's one of the groups that we have within the APC. My full-time role certainly is with EFL. EFL is a fiber optic connectivity company. Today, I'll be speaking a little bit to give you guys a bit of a brief on what APC is all about and some of the work that which we are doing in the industry. So APC stands for Advanced Photonics Coalition. And, we've basically trying to work specifically on the photonics challenge. This is something that I just alluded to just in a few minutes ago. There is an increased amount of density, and there are solutions that are needed. The challenge with the solutions within the ecosystem is the amount of differentiation, right? And the other challenge is certainly trying to bring up and technology from the grassroots level up, so that these can be standardized and can be adopted into the industry. So we work across the ecosystem. We work in terms of, getting requirements together, down the ecosystem and getting all the technical input on how that could be implemented, and really going out in the industry and lowering some of the barriers as far as new technology is concerned. One example is certainly the multi-core fiber working group that I'm chairing right now. And we do have additional working groups, which I'll be talking about in just a second. So I think very excited to be part of this group. We are a growing group that has made some very significant advances in the last few months. We have grown every month since we launched. Many thanks to Melissa and others in the team. This is the group of companies that are part of the Advanced Photonics Coalition today. You see a very significant number of names there in terms of who's participating in these groups. We are working on multiple different working groups as well as we build our standards, ecosystem-driven standards. Here's a snapshot on the executive leadership. The APC is actually led by Jeff Mackey. Jeff is out today traveling, and I'm helping him out on this introduction today. We have Julie Adams, who is with IBM and the working group chair for Silicon Photonics. We have Jake Chu from DuPont, who is the treasurer of the board. Melissa certainly helps us on lots of different areas, including membership and other activities. Joshua from Heroes A, he's our interconnect, optical waveguide interconnect system working group chair. You see my picture there. That's me on the multi-core fiber side, and we have Vikas, who is from Global Foundries, who's also the board of director for APC. And last but not least, we have Brian Hall. Brian helps us host a co-packaged optics working group. He is with Colorchip. So I think we've made some great progress with the number of participants we've had in the APC. We're continuing to work on the Photonics challenge in trying to address what's required by AI and building up standards. More information on the working groups itself. The Silicon Photonics manufacturing. This is low-cost manufacturing, right? This is hosted by Julie Adams from IBM. Rack density management, all about multi-core fiber. Multi-core fiber basically gives you 4x the amount of density that you have in the current single core, and compared to current single core. So you also end up saving about 75% less materials as well. So this is a multi-core fiber working group. What we're doing here is coming up with solutions, specific solutions that can be used both in the transceivers and CPO. And we have a charter that's actually getting some voting right now from the members, and we're going to continue to work in terms of defining what some of those solutions could be in terms of adoption into the industry. The co-packaged optics working group, this is hosted by Brian Hall. He's looking at how to solve the challenges and how to have better adoption around co-packaged optics. Co-packaged optics, as many of you know, has been around for a while. We are trying to take a look at it from the point of ecosystem driven by the companies to reducing differentiation, finding more common standards, and building this up. And certainly, Joshua Kim has been hosting the optical waveguide interconnect system group, replacing copper, where he's done a significant amount of work over the last year and a half and more in terms of where we see photonics playing a very important role, especially in the AI landscape that we are in today. So these are the working groups. I encourage you all to please join us and in these working groups and be part of these standards. It's very exciting. You can certainly reach out to me or Melissa, and we'll be happy to enroll you guys on and grow our participation as we go about building more and more of these standards. That's all I have, Jose. I will pass it back to you. Thank you very much.
Congratulations, Nick, on everything that you and the entire APC coalition is achieving. Bringing these 4 working groups on the silicon photonics, on the fiber, on the interconnects is something that is bringing all the industry together, and that's what it's all about. Thank you for working on that. Thank you very much for also communicating everything that you do on this. Let's now talk to one of the board members of APC, one person who has been, thanks to his work, advancing global foundries and silicon photonics together. It is such a huge achievement by this industry, having silicon photonics manufacturer global foundries at this scale and with this seriousness. Vikas Gupta, Thank you very much for being with us today. Tell us about the Silicon Photonics platform and tell us how all of us can help. Let me add one point for everyone that is in the room today. We have right now 118 participants. During the meeting, you can post questions using the Q&A button. Post your questions there to make sure that the speakers today can answer them. In your question, please write your name and company because that gives context to your question. And now, with that said, Vikas Gupta, the floor and the attention of everyone is yours.
Thank you, Jose. Hi, my name is Vikas Gupta. I lead the product management team for Silicon Photonics at Global Foundries. And today, I guess you're going to go through a lot of presenters who are going to give their point of view for that specific industry that they represent. I'm representing the foundry side, and so I wanted to give you all a view of things that we are doing from the foundry perspective to enable high volume and robust volume manufacturing for photonics. So I'm going to start off. I'm going to cover sort of three aspects. The first thing is just creating a flexible foundry platform. Then I'm going to cover topics associated with wafer level processing and the need for a vibrant ecosystem. So starting off with my first topic, as a foundry, in order to meet the scale for AI-based, photonic interconnects, there are multiple options for, scale-out networks, which tend to be more standards compliant, versus scale-up networks, which tend to be, bookended solutions. And it is important for a foundry to be able to offer a technology that covers that design space where there's co-packaged optics, pluggable, scale up, scale out, and offer that sort of foundry solution that can be applied across the board for these solutions. And the value to the customer that we bring as we create this sort of feature-rich and flexible technology is the fact that learning can be applied across these solutions. And it helps the customer from a yield perspective, and for a foundry, it provides the scale. And so for Global Foundries, we have offered GF Photonics as our foundry platform, which is a very rich platform, but it's also extremely flexible that we can address all of these solutions. But depending upon the customer system architecture, we can offer a monolithic solution or a photonic solution. Monolithic means that we actually integrate, the RF CMOS along with the photonics. And in some cases where a company may want to do a design with a separate EIC, we support those sort of solutions also. And then within the context of the technology, we offer a lot of flexibility to our customers in allowing them to do freeform designs. And the technology actually is able to comprehend these sort of customer developed solutions that we can offer as part of the silicon solution from the foundry side. In addition to that, I've already mentioned this, the slow wide or fast and narrow, and that is sort of related to the scale out, which tends to be more of fast and narrow, and the scale up, which will probably be, proprietary solutions, which tend to be slow and wide. So this is all inbuilt into the technology through the device offerings that GF Photonics offers. And then, the need for varied fiber attached solutions. In some cases, there's a need for permanently attached fibers. In some cases, there are detachable solutions. So it is important for a foundry to be able to comprehend these sort of aspects of a system requirement that the customer may need. So putting all of this together allows the foundry to offer scalable solutions and also achieve volumes that are required for cross product learning. The second aspect, in order to meet sort of these scaling requirements, is to do everything that we can at wafer level. So one of the trends you will see, as even from an OSAT perspective, a lot of the advanced processing for packaging that is occurring more and more at wafer level, whether you start from plating, which is, for bumping requirements, TSV reveal, wafer sort, and that is electro-optical testing. There will be several vendors and presenters in this webinar, which will talk about wafer scale solutions for electro-optical testing for functional. So as the cost of the packaging becomes higher and higher, you actually want to be able to weed out and address yield level issues at a wafer level. So more and more work that can be done at a wafer level, the better off you are in terms of reducing the cost, but then also scaling up the solution. And we also want to go to the extreme of doing some of parts of the fiber attach, if possible, at wafer level also. So some of the detachable solutions, you can actually start doing turning mirrors and things like that at wafer level. So the more work you can do at wafer level, the better scalable the solutions tend to be. And then the last topic that I wanted to cover is, none of the companies in the ecosystem can do all of this work by themselves, and it is important to establish a vibrant ecosystem that the foundries can work with, but also the customers can work with in terms of finding solutions. And that starts from design partners, packaging partners, and EDA partners, including, going out to the vendors that are providing lasers, that are providing SOAs, fibers, connectors, etc. So part of this enablement of solutions for the AI market does require a larger ecosystem. As they say, it takes a village to raise a child, but in this case, it takes a village to raise these sort of solutions. So I think it's an important part for us to have A, flexible technologies, B, flexible technologies, a lot of the wafer level packaging and testing if possible, and then a vibrant ecosystem. So that's my presentation. Thank you.
Thank you very much, Vikas. What would you say are, in your opinion, the biggest challenges that the silicon photonics fabs are facing today coming from this so-called AI revolution?
Yeah, so I think in the past, there have been a lot of varied solutions that are provided to foundries, which was subscale in terms of raising. I think, at least I would say from our side, the fact that we have a flexible platform, we're able to minimize solutions that customers are providing on a technology level. I think there are still solutions that are being provided at a packaging level. And the more that we can standardize some of the packaging options, I think the better off everybody will be in the ecosystem to find solutions that are scalable.
I think one of the biggest challenges that we always have with the photonics integrated circuits manufacturing is how to, after having the chip manufactured, how to package it in the right volume for the right cost. And there is where Global Foundries, you are working as part of this working group together with our next speaker. I would like to welcome Alex Janta, who is the lead scientist and lead business developer for the packaging and assembly line at IBM Bromont. And we want to hear from them how we can package those silicon photonic chips manufactured at Global Foundries reliably and affordably. Alex, thank you very much for being with us. The floor and the attention of everyone goes to IBM.
Thank you, Jose, for the introduction. So I'm Alexander Janta from IBM. I'm a senior advisor engineering for heterogeneous integration in photonic packaging. And today I will present some of our IBM semiconductor work that we're doing on advanced photonic packaging technology for the next generation AI. So sorry if the slides go down smooth. So of course, IBM Semiconductor is leading in advanced packaging technology. And today I will mostly focus on chiplets and advanced packaging. So what is needed for co-packaged photonics dies close to ASIC dies or generative AI platforms. Of course, IBM has a full advanced packaging infrastructure from IBM Research to IBM Albany, as well to the high volume manufacturing from IBM Bromont. In fact, IBM Albany has this great platform for 300 millimeters. So they can support 2.5 3D packaging, C4 microbump, hybrid bondings, RDL, advanced bonding assembly, and thermal characterization. Here are some example of products that are assembled at IBM Bromont. So this is the advanced packaging site. And as you can see, more and more, we will see optics coming towards the ASIC, since there are more power efficiency and also the bandwidth requirements that are required. This is the photonic value proposition. So of course, there's the IO starving. And as we can see on the bottom right graph, there's a gap between the compute and the interconnect to the bandwidth or the RAM. So as you can see, we need to close this gap, and silicon photonics and co-packaged optics can answer those, support those multi-terabit bandwidths with low power, and of course, be able to scale the AI and machine learning required. Here you have a little table. I won't go very through, but you have some composition between the power, the cost, the density, and the reach of the RDL, interposer, fan-out packaging, the memory with HBM3, the various UCIe standards, the PCB, the electrical cable, the NVLink, and electrical socket, active optical cable, front pluggable, oboe, and so on. And you can see how CPO positions against those. And you can see that the main driver is also the power efficiency and the density in terms of the bandwidth that can be achieved. Of course, IBM has a full advanced integration. So basically, for all of those little pictograms, you have a department regarding designing package and co-packaged optics from a switch ASIC to the photonic die. And of course, packaging is critical for the success, and all need have to co-design mine. And of course, we can work with their customers to enhance the target application and needs. Of course, IBM offers a full turnkey solution. So from the electrical PIC assemblies to the optical interconnect attach, the CSUB test, and the overall more complex system and package, so the more complex MCM switches or AI platform where we can co-package optics, and here I have some pictures and example, up to the final optical module test. You have here some graphs of scheme of integration. So you can see how the photonic die and the electrical die can be co-packaged. And as we see, we're going to see more and more those 3D packaging as we're going to have an increase in bandwidth speeds. I will let some time to this animation. So of course, IBM has made this press release. So we have this amazing breakthrough in kind of bandwidth density of optical interconnects. So as you can see, I will show you on the next slide. We have this great optics on package. So we have this high density pitch for optical interconnects, up to 108 channels per connector. And this is a breakthrough. It's like 6 times better than state of the art. And we can have a better power reduction as well. Of course, IBM is also working on the supply chain. So we have all our suppliers all over the world, and we try to have a strong supply chain, and we also have 100% North American supply chain available if required. I have also to mention that we have some great announcement at the IBM Bromont, so the packaging site. We had some help from our governments to help this CPU assembly line. So we have a huge investments, and we are scaling our plant's capability mostly to support those generative AI and high performance computing that will use CPU assemblies. But still, one main gaps is still the test, and here you have a little overview. So it's still the test is still a lot needs a lot of work and collaboration. So of course, the methodology, the module test connectorization, the standardization of that, the sub-assemblies test as well, the electrical optical flow, the calibration times, the system level tests, and the burn-in and inclusion of MCM's SCP, because as you know, those co-packaged optics and AI platform will need to have very robust and reliable interconnects to support the workloads. So we believe burn-in and some HTOL validation on the CPO package will be required. Also, we need some JEDEC reliability for the CPO, as the photonic die will be close to a hot ASIC, and we need to have some fit rate demonstration to be able to scale that, and mostly for those next generation hardware that will be in data center that will be able to distribute the memory, the compute, and have some bandwidth steering. So you can see that there's a vast ecosystem from the photonics co-design, the optimization to the system design, the electrical, and everything is driving for the packaging with all the various form factors. So all the optical interface, the electrical and interface as well need to be more standardized to be able to help the overall test platform optimization. Currently, it's too much, how we say, customized for each customer. So we need more standardization. And we need also to acknowledge that this is a co-optimization effort at the system level. So all the power efficiency, optical budget, and health monitor, and redundancy, replacency in the system level needs to be taken into account. And then at the end, you also need to have the cost structure. So we need high volume manufacturing adoption. We need to have some rework repair strategies, and also take a look at the assembly and test economics, because in co-packaged optics, assembly and tests are our main driver of the overall package cost. You have a little table of our readiness. So as you see, we have a lot of reliability data, and we have great packaging technology to do co-packaged optics. So we have the right assembly techniques and demonstration for high level reliability. So in conclusion, packaging is one key critical success for the next generation AI. IBM has a great co-packaging toolbox. We can help for design for effective manufacturing. We have this assembly design kit that can help you to design your PIC and make it compatible with your assembly ground rules. We have single mode photonic assembly that are WDM compatible, and we basically leverage our microelectronic know-how and infrastructure to achieve high volume manufacturing targets. And all our packaging are compatible with high throughput microelectronic facility. So if you have any question, please don't hesitate to contact me.
Thank you very much, Alex. Thank you for a great presentation, and thank you for the evolution and miniaturization of CPO. What are the biggest challenges that we have right now? We can do, as you said, co-package is not really a new concept, and we've been working on it for many years, but now we have a challenge because companies such as NVIDIA are showing that this is the future for them. What are these translated into the assembly and packaging?
We need standardizations, mostly to support high volume manufacturing. We need more standard electrical interface and optical interface for those co-packaged optics. So we need to have those clearly defined in order for the next generation AI and our hardware infrastructure. We need to have this basic framework, and also to help in the test portion, because we believe that the test is a critical part, and having some more built-in self-tests and self-diagnostic on the photonic package will be very useful.
What do you want to standardize? At the end of the day, I mean, when you talk about a CPO, this is only a concept. Every company will make their own. Are we looking for standardization with the fiber ins and fiber out? Are we talking about the pitch? What would be the three top things that you think APC should standardize on this aspect?
So the connectivization impact, the electrical speeds, we see the various electrical speeds. For example, those big switches will need higher speeds than those more efficient data motion devices that will probably run on lower electrical speeds. So all those interfaces need to be standardized and correctly assessed regarding the pitch, regarding the form factor, to be able to include. So for photonic chiplets is a great topic. So we see that UCIe is now working on those photonic chiplets and try to standardize them. So that's also a good way forward.
I would like to now, of course, keep encouraging people to write questions in the chat. We have actually received quite many questions, so many of them actually related to the slides. I would like to remind everyone, rest assured, if you register for this event with the email without typos, in your mailbox you will receive the slides in the coming hours. But now let's continue. Thank you very much, Alex, for a great presentation. When you have the chip package, then you want to make sure that it has the right system engineering to put in systems globally. And for that, there is a company in our ecosystem that is active in almost all the markets related to semiconductors. I'm talking to the giant Jabil, who today is represented in the room by Giorgio Cazzaniga, product manager and director in Jabil Photonics. Thank you very much, Giorgio, for being with us. Tell us how you're going to get the chip from IBM in Bromont, and you're going to make sure it is scalable and it is in volume production ASAP, because we need it now. The floor and the attention of everyone goes to Giorgio, goes to Jabil.
Thank you, Jose. I will try to answer your question. Of course, it's not so easy and straightforward, but I will try for sure. Yeah, so my name is Giorgio Cazzaniga. I work as a PLM leader, senior director in Jabil Photonics, meaning, let's say, product manager for products, but as well capabilities. And today we are speaking about capabilities. The first slide I would like to comment first is, okay, taking as example the CPO, that for sure in AI is becoming important application of PIC and silicon photonics PIC, which are the targets, and let's say what are the impact in terms of manufacturing and where manufacturing can help. So I distinguish in this table, let's say, some of the parameters getting some of the numbers coming from OFC. OFC was a great show. There were a lot of presentation, but also a lot of information shared. For example, for what is concerning AI and CPO, distinguishing between the scale out and scale up application, we see power consumption as one of the first goal, where the scale out likely could have a 5-6 picojoule per bit target, while for the scale up is much more aggressive, going 1.5 petajoule per bit. But also in terms of cost per bit, the scale up, at least the targets would be very, very challenging. So 1 cent per gigabit compared with maybe 10 cents or 20 that could be the scale out target. And the target here is to have a solution in the market quickly. So it means that one of the targets is to decrease the time from the design to the mass production. So really to go from years to months. So when we speak about manufacturing, in particular, the second and the third aspect, so let's say the cost and the overall cost per bit and the time to market are important aspects we are considering, we have to consider. Let's also let's say get a common, let's say, background or common understanding of what we mean, for example, for a CPO solution, which are the building blocks. So the first one is for sure the interface, the electrical interface. As just mentioned today, there are some standard like UCIe that is becoming standard for chiplets, but also for PIC when connected to, let's say, in a CPU application to an electronic chip. But also other applications require maybe different standard, different rates. And so this for sure is one of the topics, because different rates means different maybe packaging requirement. The second one, let's say not less important, is the fiber attach. That is an important point to define, but as well to, in terms of manufacturing, to perform. Today there are detachable unit, there are fiber unit, not detachable. So different, let's say, activities, different processes defined for the different technology and different solution. The third aspect is the laser. There can be solution with internal laser or external laser. In case of external laser, becomes another building blocks in the subsystem. That can be a PCB, can be a board. In case of internal laser, becomes instead something that should be attached at the wafer level or the chip level. So becomes again an issue on photonics packaging. And finally is the attachment between the electronic and the photonics. So as mentioned also in previous contribution, how to attach, for example, a silicon photonics PIC through, let's say, with a linear driver or with TIA using, let's say, different bumping architecture, different 2.5D or 3D architecture, and eventually also converting and having also some electronic chip that convert the rate that is used externally. So for example, the UCI to the internal rate. So all this stuff, again, are manufacturing related. Each of these elements represent a cost. So first of all, what we are doing as Jabil, and then we will go through some points related how to ensure manufacturing to be really robust. That is one of the topic of today. So if we look to the, let's say, the global, let's say, life cycle of design, we are not doing as Jabil a design, and of course there are many companies doing a different design. We are not a foundry, so we receive a foundry, we receive, let's say, wafer from foundry. Sorry, with this pointer is a bit difficult, but anyway, and what we do in Jabil is mostly to start at the wafer level, including wafer level processing, including, let's say, dicing, back grinding, and as well testing. And then once the chip is diced, what we do is that we use this chip in the context of the application, including activities like flip chip, like attachment of fiber or lens and fiber, attaching lead if it is the application, and testing, and then delivering to the subsystem level. That can be a board, can be a blade inside the system, can be a module, can be a transceiver, PCB, and finally delivering the full, let's say, system with integrated, in this example, in this case, CPO. So these are, let's say, where Jabil can contribute and can be, let's say, also complementary to the other companies. But if we now look to be robust, what we have to look in particular for what is concerning cost are different factors. And I'm not looking here to the BOM cost. The BOM cost depends from the wafer, so from the foundry, from the fiber arrays, and from the real material. What I'm looking here is more to the manufacturing cost, in particular to the items, to the parameter that are typically the impacting the cost, that are the yield. And the yield depends a lot from the process. So a good process definition can bring to high yield from the beginning. A bad process can start really with very, very, let's say, low yield. Consider simply that with 50% yield, the cost becomes double. So it means that you are paying 2 times if the yield is very bad. The target is always to be, let's say, 90% higher. So it means to try to reach the, let's say, 95% or more. But of course, at the beginning could be really an issue. And in particular, if the process has not been defined. The second point, and is also about yield, is to choose the right process option. For example, one of the topic we always touch is the epoxy selection. That is critical for yield and as well reliability, because once you define a certain recipe for, let's say, a product, how to attach fiber or how to attach together the different components, then you need to be reliable. And so this can be an issue for critical, let's say, for yield, but also for reliability. Second parameter is the efficiency in terms of unit per hour. Again, reducing the cost means increase the throughput, so means the unit per hour. And in this is important what we provide as contribution in terms of automation. Automation is an important step in order to avoid, of course, touch points, and means reduce the unitary cost, but as well test. And test has been mentioned as well as a key point, because at the end is a trade-off. You need to be reliable, you need to have an high quality, but on the other hand, you are not to forget that you cannot impact too much the unit per hour. And finally, the investment in terms of capex, in the sense that each investment to produce is, let's say, impacting the cost. And to minimize that, is important to have, as also mentioned, a standardized process to avoid to have a specific capex, means machine for specific projects, but as well to have at the end high volume, because the capex is minimized, if you want, is absorbed as much as the volume is high. So these, if you want, are, let's say, 3 parameters that we consider important to get the cost down, and so to reduce, let's say, the final price in the market for the application. But trying to answer instead the question about the volume scale manufacturing to be robust, what we see as well is that there are choices that are taken in advance in the life cycle of the product that can impact later the fact that the design is robust enough to be manufactured at the right cost. For example, at design level, using standard building blocks, maybe, maybe having some trade-off with performance is sometimes better than having the best performance, but having a product with difficulty to be manufactured. Try to use existing solution for the most complex issue. For example, the fiber attachment and the metal plating are for sure 2 critical aspects. If you define a very specific process for that, you can maybe either have a longer cost, longer lead time, or a higher cost. And for this is important at the design level, or also to think about the trade-off between performance and manufacturability. In the second phase, typically after design, that we can call MPI, one important point is to define the same recipe at this level respect to the one that will be used in the large-scale manufacturing. And as JB, we think this is very fundamental. For this reason, we have opened in Ottawa an MPI center for photonics packaging, where we replicate in a small volume what we can do then in the large-scale manufacturing sites. The other point is to perform what is called design for manufacturability and design for testing. This phase, done an MPI phase, allows you to solve the issue that can be later big issues. And then that is a bit connected with the first one, use the same machine for the large-scale manufacturing. Finally, the aspects that are strictly related to the manufacturing, so when you arrive to the manufacturing phase, is really to, let's say, improve the yield, so to have, let's say, the capability to increase via the yield, and automatize in order to decrease the overall cost. Thank you for...
Thank you very much, Giorgio. We actually have questions in the chat, but the first one I think is actually for me, so I'm going to answer it. See, who are the standard vendors for the UCLE platform? I mean, let me know that you're talking about the chiplets. The standard vendors, we all know them. They are NVIDIA, Marvell, Tenstorrent, Intel, AMD. But if you are talking about an optical chiplet, actually the only one, the world's first UCLE, is from IR Labs. It's the world's first, and they are going to present it later in the next presentation. But before we do that, Giorgio, we have a couple of questions for you. The first one is actually quite difficult for you to answer because there are many. Where is Jabil's CPO assembly site?
Yeah, so today we have the MPI site in Ottawa, where we do, let's say, the process definition, and the large-scale manufacturing is in Malaysia, in Penang, where we have the Photonics, if you want, site.
The second question could be for you, but also for Alex Yanta. The question is, what is the preferred fiber array platform? Polymer, plastic, silicon V-grooves? The form factor and cost is sensitive. Is silicon V-groove attractive as cost-effective option?
Yeah, so it's not easy to give, let's say, a black and white solution, because again, this is an example where we can have a different solution solving some issues, but maybe creating other issue. So it's not easy to compare here, but for sure what needs to be done is a comparison not only at the performance level, but also at the manufacturing level. Means, let's say, the time needed to manufacture photonics, what is needed in terms of machine, the accuracy, so what you need to do, and then the final yield that you can achieve.
Maybe I
The
can
final question.
add to the comment.
Sorry, Alex, go ahead.
So Silicon V-Groove has the advantage to shift the packaging complexity to the wafer, and you can have self-alignment and extremely high throughput assembly techniques. So this is very appealing. And then based on your application needs and density, then you can have some polymer waveguides that have like 51 optical per millimeter bandwidth capacity, and they're still high volume manufacturing compatible. So basically we have to look at your application. What is your foundry section? GF has a great V-Groove platform where we can package optical fiber quite efficiently. So we have the right packaging solution. It's a matter of your application, and this will steer you toward the right optical interconnect technology.
Thank you very much, Alex. So silicon V-grooves are attractive as cost-effective options. The final question, again for you, Giorgio, is what are your thoughts on detachable fiber regarding fiber arrays?
Yeah, so when you go, let's say, out from the single PIC itself, but you go at the system level, for sure detachable optics has a big advantages. Why? Because if you want to have and to use your SMT line that you use for the typical electronic mounting, also for the PIC, it's very difficult to do this if there are fiber attached. So instead, if you attach, let's say, what we can call the socket, and then you use a detachable optics, is much more easy. So this for sure is an advantage from the overall process for the CPO in particular, to mount a large quantity of fiber around the Ethernet switch or whatever it is.
I am extremely optimistic that we're going to have pluggable fiber arrays for CPO. I believe there is no other way. But thank you very much, Giorgio. Congratulations on everything you're achieving. And congratulations to the next speaker. I think this one is for me my favorite presentation today. A month ago, a company in the United States, IR Labs, shocked the world with an announcement, 8 terabit per second bandwidth on an optical chiplet. Since that announcement, everybody has been wondering how they do it. And today, I'm not going to say they're going to tell us how they do it, but they're going to tell us what they do. Scott Clark, thank you. First of all, congratulations on everything that IR Labs is achieving. And thank you very much for being with us today. The floor and the attention of everyone goes to you.
Well, thank you, Jose. That was a terrific segue. As you mentioned, at OFC, IR Labs, we did demonstrate the world's first optically enabled UCIe chiplet, closing a full link at 8 terabits per second. And IR Labs, we're a fabless semiconductor chiplet company, but we not only do EIC, PIC monolithic chiplet, we also have our own laser light source solution that together we call an optical I/O solution for integration. We've been at this for a number of years. IR Labs as a company is celebrating our 10th anniversary this month, but we're still very much a fast-paced startup company in just an exciting space right now. To really address the question or the topic at hand, really, as a fabless semiconductor company, we see that getting to a known good die is the critical enabler to getting to robust high volume. There's a few challenges in this. But first, just in the last 18 to 24 months, a lot of things have shifted. What we've seen is a shift from questioning the viability of the technology to more of an acceptance. And now there's more discussion and topics around solutions and implementation and scaling of these technologies across the board for the entire ecosystem. So within that, the industry, we're in a deep into the learning curves in multiple areas, as some of the presenters have raised. There is just the inherent silicon design, right? And figuring out some of the design approaches. There's the foundry PDK and the foundry process and the maturity that goes through. There is a chemical and material science as well that not only goes into the wafer processing, but then everything into the packaging, the substrates, etc., to make these solutions work. And then finally, a large area that still needs to be addressed and is being addressed is in the area of test, not just at wafer and die, but also at package and system level as well. So all of these are these industry players are jumping in and addressing these. We're very rapidly going through this maturity learning curve. And it's exciting. It's exciting to see because it's coming together very, very rapidly. So all of these elements do contribute to higher yields and getting to tested, qualified, known good die that allows for robust volume manufacturing. And again, as I said, we've seen significant progress in all of these fronts in just the last 12 to 18 months. And IR Labs is working with many of the panel speakers companies here today. So we can't really ignore what happens after we get past silicon. So once we get to KGD, there's another challenge that a lot of the speakers have kind of raised. And that's more associated with the back end and bringing this entire solution together. So there are challenges that are being addressed, as people like Alex and Giorgio have pointed out, in advanced packaging. Laser light sources. IR Labs today has their own 16 lambda laser light source that works with our optical chiplet. But we do see large laser companies now starting to step into this realm of high density laser light sources to support these optical technologies. As was just addressed by Giorgio and Alex alike, we're now getting into fiber attach solutions, whether it be, say, V-groove based direct fiber attach, and now detachable connector solutions as well. So we're starting to see those solutions come to the forefront, and it's very much needed to make the solution work within a manufacturing realm as well as for field serviceability. And those detachable connectors are coming in both grating coupler and edge coupled solutions as well. And then finally, again, once you integrate this silicon and you're at the MCP level, managing that optically enabled MCP through a board manufacturing flow as well as a board build and system level flow, this is where more and more electro-optical test solutions are required. And so we truly need a robust, high volume enabled back-end ecosystem to enable the front end of silicon. So as I mentioned before, we are collaborating with a lot of the companies that are on this panel. These are some of our partners. We've partnered with foundries, OSATs, detachable connector companies. We have a lot of different development and strategic engagements And we're championing this collaboration, industry collaboration across the OSATs and EMS partners to enable this high volume, robust ecosystem. And then finally, Jose, as you mentioned, yes, at OFC, we did demonstrate the first optically enabled UCIe chiplet. That was exciting, and there's much coming from that. For any of the attendees, we do offer to collaborate, and we want to bring forward solutions into this realm. And I'll hand it back over to you, Jose.
Thank you very much, Scott, and congratulations on everything that you are achieving. I'm extremely happy and proud that you keep choosing Optic as a platform to make these huge announcements that are shocking the industry. There is a few questions for you, but the first one is coming from Alex Guichard. He's wondering, what kind of short line density can be achieved with the 8 terabits per second solution?
I'm going to reserve from answering that directly because it really comes down to packaging approaches. Now, and that really comes back into, is it a single monolithic chiplet? Is it a 2-chip solution? And it really, the answer varies depending on how you're approaching the packaging, the packaging challenge. And we see customers trying to approach with different packaging approaches. And this ties back to, I think, Vikas and Alex's points on the need for standardization on the packaging. Today, I see it as quite fragmented. People are trying to figure out what works and what is best for their applications. So there's no one cookie cutter answer that I could give to that question right now.
I think you already gave between the lines the answer, but that's okay. Let's go to the next question. Like this one is a visionary question. I warned you here, Scott. Like electrical power source. Why can't we think about power box that supplies lambdas to boards and racks? And Shankar is wondering, high density laser diode arrays are great, but they are dedicated to a single socket or board.
Jose,
can we think about your chiplet as a sort of power box that instead of giving electrical contacts provides lambdas to boards, a multi-wavelength solution?
So are we suggesting of integrated lasers?
It is a very visionary question. I think actually we could formulate it better. Allow me to answer him privately, but this is of course more or less what the interposer solution of IR Labs does already. And the last one is from our friend, very good friend, person from Color Chip, Brian Hall. Brian Hall, thank you very much for being with us today. Brian has a difficult question for you, but you have to give us an answer, Scott. Okay. Which material is your interposer and what is the maximum dimension?
I'm going to refrain from answering that one as well.
I want you to say glass, you know that, it's color chip. Okay, next question, Andy Sang. Are you going to comply with the CWWDM MSA for light source choice?
Yes, absolutely. We're an MSA member and very much we support that standard.
People are trying to rephrase Shankar's question. Allow me to answer this in a different context because it's a bit a visionary question. Scott, what you're doing is really fantastic. Really is. I am really proud of having you in the ecosystem. Congratulations. Allow me to bring Alexander and Giorgio back in the room because the next two questions are for the two of you. Ala Omer is wondering, what is the typical loss budget, propagation loss in the fiber to chip? Alex, do you want to venture a guess before I say 1 dB?
Yes, we have achieved 1 dB. Typically, the budget that people are counting is like 2 dB for the optical and the overall variation. But yes, the typical insertion loss is 1 dB with a 2 dB budget currently.
The other question is about the through glass bias, I suppose. Do you typically do routing on a single layer or do you have solutions from layer to layer? Giorgio. Allow me to get back to you on that question, but yes, Giorgio, there's a question for you. Do you typically do routing on a single layer, or do you have solutions for layer to layer?
Typically, it's on a single layer, what we see today. I mean, then Depends on the evolution, but typically single layer.
Single layer is the answer. Congratulations. And we continue with the fantastic program. So far, I'm really happy. We are finding out many interesting things. The next speaker is a fantastic speaker. However, he has a fantastic allergy problem. So he cannot be here today. The company Quantify Photonics is here to help us testing chips at ultra high bandwidth. And of course, I would like to wish Case Popstra from Quantify Photonics a prompt recovery. We are missing you today here. Your presentation would have been spectacular. I wanted to acknowledge that you were registered for the meeting. And with that said, let's continue and let's go to the final presentation before we do our final discussion. I want to go to the company Teradyne, represented today by the Senior Director of SoC Product Strategy, George Hararte. George, thank you very much for being with us today. The floor and the attention of everyone goes to our last speaker today, Teradyne.
Thank you, Jose. Can you see my sharing? Yes?
Yes, we do.
Great. Welcome, everybody, again. My name is George Hararte. I am Senior Director of Product Strategy at Teradyne Semiconductor Test. Teradyne is in the business of testing the world of semiconductors, from high-performance compute devices to power semiconductors for electrical vehicles, memory, wireless. We test everything, but we test in high volume. So we're in the business, really, of prototyping in high volume semiconductors. So my colleagues here in this panel have already explained in different angles, from different angles, the value proposition of silicon photonics or photonics ICs. I'd like to put things in a different perspective. Clearly, the data centers, HPC data centers, as shown in this slide, are complex. Not only complex, but they're expensive, high cost. And the key requirements for this type of servers, clearly high performance, high reliability, bandwidth, speed, latency, power. They're expensive, they're complex, they need to be reliable. In fact, they're so expensive that people go serverless computing, meaning renting per second, this type of systems. Clearly, test is important. We cannot have a new photonics device that goes into the systems fail, and then you have to throw away a huge system. That's not about good value proposition. So testing is important. Teradyne gets to basically judge good or bad in terms of the chip. And that's a big responsibility, because if it is good but it's bad, that's a quality problem, a reliability problem. And if it's bad but it's good, and we declare bad but it's good, it's an economical problem. We throw away money, if I make the point. So the value proposition of photonics is already explained, and we looked at it from different angles, right? The bandwidth, advanced packaging, power consumption, space, and so on and so forth. So you have this slide. I will not go through it one more time, but it's clear that it's here to stay for the long run. Let us now define what is an optical engine and a CPO, co-packaged optics. This is important because we need to define the test insertions that we need to support in the ecosystem to declare a chip good or not good. And the optical engine versus a CPO, the basic difference really is the presence of a compute device, whether or not it is a switch or in the future, perhaps a GPU or XPU. The basic difference is the fact that we have a switch device for data center, which is a really high digital device, surrounded by multiple transceivers, so-called optical engines. So clearly, this device, which is very expensive, surrounded by lower cost type of optical engines, needs to work, and needs to be reliable. And a trade-off between throughput and quality is always important. So here we are now in a relatively simple optical engine as it relates to the optical and electrical, going into a very complex type of CPO type of package. So this brings us into the question of what are the possible photonics, in this case, silicon photonics, and co-packaged optics test insertions. My colleagues have talked a lot about the front end, but they also made a point that the back end needs to be ready in high volume manufacturing testing. And starting with the wafer test, there is currently two approaches. Approach in which the photonics and the electrical are all in one side of the wafer. That's one foundry approach. And the second foundry approach in which we bond an electrical and a photonics. So that means that we have to be able to test from both sides, top and bottom. That requires a high volume probing solution and alignment solution to be able to make contacts both electrically and in the optical side. Then there is a question is, do we singulate the die and test it at the die? That is an important question that we are obviously in the process of, as an ecosystem, answering. And the reason this is an important question is when we go to the CPU module, this is very expensive. We cannot throw away, $2,000, $3,000 type of chip or higher. In the case of basically pluggable modules, the cost of a pluggable module compared to the cost of integrating the optical engine in the switch, making a CPO, is significant, orders of magnitude different. Perhaps when we went the optical pluggable module here, will be more like a throwaway. If it fails, well, replace the cable, the fiber cable, replace the two ends, so to speak, of the entire cable with the pluggable module, so you're done. But we cannot throw away and replace the CPO module. That would be too expensive, not economical, and basically a wall to high volume manufacturing of CPO. So we got to be thinking, one is to be tested in the automatic test equipment, one is to be tested perhaps at the circuit level, and then at the end, what goes into the ATE or SLT. And there is multiple tests that need to be done. Main point, we got to have non-good die before we put this into the CPO. So that brings the challenges. In the old days, so to speak, maybe 2-3 years ago, in lower volume, some of these challenges were, let's say, tolerable. But now we got to find solutions. At the wafer level, for example, not only we had to test optical and electrical signals, but this point here of aligning the optical fiber with the wafer is significant. Just aligning the laser source to the optical, to the photonics IC used to take minutes, many minutes, and the other 2-digit minutes. Needs to go into 1 to 2 minutes less into the seconds to be able to make a manufacturer. So, companies like Photonic, who are doing the alignment mechanisms, are key to be able to reduce the throughput, to improve the throughput, so to speak, to increase the throughput, that is, of this type of alignment mechanisms. I already talked about double-sided probing. Then there is the high-speed digital photonics testing, that is continuously increasing. So we need to bring photonics instrumentation into the ATE side and SLT side. And then there's thermal management. I show you the anatomy of the chassis, right, of the data server. You have cooling lines coming in, all of that. So that is, at the end, all of those things need to be addressed as we go into testing. So continuing with the test challenges, there was a question earlier today about standardization. The CPO connector could be an opportunity. It's an opportunity for standardization because we had to align in high volume production the light source to the CPO connectors, and we have multiple connectors. Then it becomes not economical. That's an area for standardization. Can we really standardize the connector to be able to have a more high volume economical solution? So there's different type of applications or challenges, but I want to highlight two: alignment of the light source, with the wafer, with the optical engine, with the CPO. That is absolutely key and an area to resolve. And the other one is the integration of optical instrumentation into the traditionally heavy electrical type of test. So therefore, Teradyne, a leader in high volume manufacturing and test, we have partnered with companies like, for example, Phycontech. Recently, we announced at the end of March that the collaboration and innovation with partnerships like Phycontech enables us to deliver first high-volume double-sided test cell for silicon photonics tests. So we believe that this collaboration is key. That's one area related to alignment, double-sided. We also recognize the importance of bringing photonics testing to the ATE that has been traditionally electrical. So we have announced the acquisition of Quantified Photonics as well to be able to bring this new capability into the ATE. And eventually gives us a path to reduce the footprint of an ATE test cell by bringing photonics instrumentation at some point inside the tester head rather than externally. So with all of this type of innovations and collaboration in the industry, we believe that Teradyne is well positioned to enable high volume photonics, not only on the optical engine side, but also on the silicon into the co-packaged optics CPO side for data centers. So thank you very much for listening. We'll take some questions next.
Thank you very much, George. It was very clear for me at OFC that the major challenge for the hyperscalers to keep integrating silicon photonics or photonic integrated circuits is that they have doubts about the reliability. It is what it is. They have doubts and we can only convince them with data. It was clear in the presentation by Scott that he's talking about known good die, but we should actually rephrase that into no bad die, because we actually have to make sure that every device is tested when they leave Jabil. How are we gonna do this? You're focusing on wafer level testing, die testing, and package device testing. Is it necessary today, in your opinion, to test and characterize every single chip, die, and packaged module? And if that is the solution, is that economically feasible?
So as every new inflection point in technology in the history, right, we initially start on the conservative side. I made a point, right, that this data center CPO and its chassis cost thousands of dollars. So we cannot risk when there is a new technology just being adopted. We cannot risk losing economically. So we start conservative. We start characterizing at the wafer level, the mechanic, in this case, electrical plus photonics. So it means we had to provide the instrumentation at the wafer level, to be able to characterize it. Question is on the die package. Eventually, we go into the package end. So what happens is as we learn and volumes increase, we start scaling down, so to speak, or removing certain tests that are perhaps not needed because failures don't happen often or at all. Maybe we're going to loop back testing versus actual at speed testing. So there is an evolution that takes several years until we hit the sweet spot of a balance between test coverage, meaning cost of test also, and the quality. So cost of test and cost of quality need to be balanced, but that takes an evolution. There's a learning curve. Initially, we tend to provide the maximum test coverage at the beginning, and eventually we optimize it.
We have two very good questions for you here in the Q&A button. The first one is coming from Alina Stefan. You've been talking about alignment as the biggest challenge, and she's wondering, do you have experts in alignment?
So Teradyne's strategy is to collaborate with the best of the best in the industry ecosystem. There are companies out there like Phycontech, and others who are experts in alignment for many years. So we are in the business of providing the ATE equipment that can interface with the best of the best on the test cell. So if we find a company like Phycontech who are the experts, we partner with them. That's what we did the announcement. That doesn't mean that we internally don't also develop expertise to understand how to partner with them. You know, to speak the language of the PI context, we did understand alignment technology. So of course, you know, we will get mechanical engineers, we get alignment people who can understand how to develop together with the best of best on the ecosystem.
The next question in the room comes from Light Counting, Bob Wheeler. What about in-field reliability? Says this is a huge barrier for CPO adoption, and he didn't hear any mention.
Yeah, so I did touch on that when I showed the data center anatomy, right, that chassis, and I mentioned that reliability is important, and that's a field reliability. And that was in the context of making the point that we need the best test coverage starting for wafer probe. I think my colleagues made that point. The more test coverage we can put early in the process, you know, we'll be able to guarantee reliability. Now, the other question is burn-in. You know, do we do burn-in photonics? I think there is a trend also to bring some level of burn-in into the photonic side for this type of devices, so we can screen out early reliability issues.
The next question, this one is coming from TE Connectivity. These guys know what they're talking about. He's asking you to talk a little about passive versus active alignment. And he's wondering, and I'm wondering the same actually, is passive alignment possible in CPO?
Yeah, that's still an evolving question, right? That
allow me to venture an answer myself.
Yeah.
I firmly believe that the future of photonics is semiconductor-based manufacturing. And semiconductor manufacturing has been based for many years on passive alignment. The reason we have to do active alignment is because we need to test components individually, and we need to test optically those components. And of course, for that, we need to put fibers and detectors next to the facets, and that can only be done actively. However, as our technology becomes more mature, and in the case of CPO, this is going to happen, I don't expect us to be able to optically test every single fiber input in 128 fiber arrays. So I believe the future is passive alignment. However, active alignment is necessary for as long as we have not reliable and not 100% yield in our wafers. That's my venture guess. And with that, we have a question for Global Foundries. No, it's not. It's GF Photonics, a software tool for silicon photonic devices designed for manufacturing. Allow me to answer that offline. And I would like to say now to George, to Vikas, to Scott, to Giorgio, to Alexander, to Nick, and of course to the Advanced Photonics Coalition, thank you for a fantastic 1 hour of a quarter of entertainment, knowledge, and most important, business and collaboration. If I had to say what is the conclusion for me for this business, is that we all need to work together, because you can see that many people here in the room had fantastic technology, but no one had the full solution. And we all need to work together because our customers demand that today. Thank you very much, everyone. This was Jose Postos, surrounded by a group of friends. Until the next time, bye-bye.